Okay, welcome back to this class again, where we will be continuing the corresponding chromophoric reagents for your analysis. So, we are taking the help of chelating reagents. So, this is interesting to note over here, because we are talking about something where we are just looking for the chromophoric reagent. So, once we uttered this term, the chromophoric reagent, that means it should have something where the chromophore can take part in this particular reaction. So, these chelating reagents can also be useful for your typical absorption of color. So, several typical chelating reagents, starting from your dithiocarbazone, dithiocarbamate and dimethylglyoxime, all these are typical chelating reagents. They are very much useful for absorption. So, absorption spectrometry can be very much useful for doing all these things using a chelating reagents. And when we talk this chelating agent, definitely we can have the concept of metal ion complexes. So, we should not forget this particular part, that how metal ions are forming complexes, because this is also the corresponding backbone for your titrations like that of your EDTA titrations also. So, now we will take the advantage of this particular use of this chelating reagent for mixtures of analytes. How we can use a mixture of analytes? It can be a mixture of metal ions, say M1 or M2, N plus or M plus. It can be mixtures of some inorganic species, or it can be any other thing. That means, it can be these two can be your transition metal ions, and also these two can be your non-transition. So, we can have these two components of this thing, that means we can analyze, and again the very simple thing is that we will be applying that formula to find out this unknown concentration. And now, what is the difference of this is that applying Lambert-Beer's law to absorbance and the molar absorptivity, all everything is known for this particular reaction, because once we have this, we know that this is absorbing, that means this particular species, which is your ML or ML2 species, which is forming over there. We should know it is the corresponding lambda max and the epsilon max. So, once we know the lambda max of that particular species, which is responsible for your absorption of color, we have to know the corresponding epsilon max. Now, when we talk about these mixtures, so these two things we will now be handling. One will be C1, another will be C2, which will be concentration for this species, and C2 will be the concentration of the other species. And this can also be very much useful, because this can be there, and this absorbance, the how it looks like, will also be there if the species, that means two of the species, such as your indicator, or methyl red or methyl orange indicator. So, this is one species, we know that where it is absorbing, where it has the corresponding lambda max value and the epsilon max values, and this particular indicator, by now as we have that particular knowledge, we are knowledgeable now that with the change in pH, it will change its color. That means, the species which is responsible for your color absorption is different. Why it is changing? So, with the change in pH, if we consider that this is a weak acid, organic acid we all know for methyl orange and methyl red, this is a weak organic acid. So, this particular is present as its intact form in acidic form. So, at low acid value or acidic value, it is present in HIN, but in the basic form what it will give? It will go for deprotonation and giving HN minus. So, these are our mixtures of analytes if we do not control the pH or the medium is not buffered. So, you must have a buffered medium such that we know a pH at a particular range, say x to y. Within this particular pH range which is buffered, you have either the species present in the purely acidic form or in the purely basic form. But we know that this will have a different lambda max value, this will also have a different lambda max values. So, to detect all these things, we should know the corresponding concentration, that means the percentage of this species and the percentage of the other species. So, what will you get? We will get something where we can have the corresponding change in the corresponding absorbances. So, if one of these species, say this particular HIN, say we consider that it is absorbing at say 430 nanometer, and the other one, this anionic form, is absorbing at say 520 nanometer. So, how it will look like? So, if you have this, so it is you mark it as 430 and this mark is at 520. So, this is our lambda in nanometer scale and this is our absorbance axis. So, what we get? We get basically a corresponding absorbance like this for this particular species, that means HIN, and we will get for IN also, because the nature will definitely be different. So, what do we get? That if you make a solution of this particular indicator, the methyl red or methyl orange, at several pH values, say 5 or 10 pH values we make, all are buffered medium, and we keep on measuring this thing from the acidic medium to the basic medium. What will you find? That this particular one, because if this is for HIN and this is for IN minus, what will you get? That this particular thing is decreasing and this particular thing is developing. So, as a result, what happens basically, because this is the intersection. So, with the change in these values, we will get something where we get this particular one changing. So, we get this and we get like this, we get like this. So, it is developing. So, this will decreasing and this will increasing, and we get some point, some crossing point which is known as isobestic point, which is very much characteristic for all these things and for anything, any spectrophotometric method, because these spectrophotometric methods are also very much useful for analyzing biological samples, analyzing DNA molecules also, deoxyribonucleic acids also. When DNA is binding with some metal ion, say Mn plus, that can also be very nicely studied by this particular method. So, DNA, if we consider that DNA itself is the corresponding chromophoric reagent, it is not necessarily that it only gives you color, but it should only give you some absorption in the other range also, that means the visible range at the lower side or the near infrared region on the other side. So, if it is responsible for your absorption, what we can do? We can measure the corresponding concentration of the DNA and the concentration of the metal ion also, and also sometimes this binding product, that whether your metal ion is binding your DNA molecule or not. So, this isobestic point will be very much characteristic for all these things. Okay. So, now we will see how this corresponding application of Beer's law. Last time in one of our previous class we have started that discussing this as the total absorbance. If we consider that if you have a mixture of two M values or M plus N also, because M is one metal ion, N can also be another metal ion, or M can be inorganic species and N can also be another inorganic species, or it is the metal ion chelate and this is also another metal ion chelate. So, directly or in a straight way manner we apply the corresponding Beer's law for that, and the formula for that will be this, that as we all know that is all these two absorbances, that means A1 and A2. These two absorbances are nothing but A1 is for the corresponding absorbance, the total absorbance if M and N plus present. So, this magnitude is the total absorbance of M plus N at lambda 1. A2 is the total absorbance at this particular wavelength for M and N. So, how do we know? We know that the corresponding A1 is nothing but, since these two are additive, so it is the corresponding individual absorbances of M1 species and individual absorbances of N1 species. What is this M1? M1 is the absorbance of M, as we all know that this has maximum at lambda 1, but minimum at lambda 2. So, this is the corresponding absorbance of M at lambda 1, and this is the corresponding absorbance of N1, this magnitude, this N1 at lambda 1, such that we get the overall absorbance over here with added up with this magnitude of his. Similarly, for absorbance 2 also we get is epsilon M2 BCM. So, this is the absorbance for this particular one, where this particular one we get this absorbance of the individual component, that means it is the absorbance of M2 species, M species at lambda 2 and N species at lambda 2 also. So, these are the two absorbances at this particular point. So, absorbance at lambda 2, but these are the corresponding sum. So, what we should know now, because earlier we are talking about the corresponding lambda max values related to your epsilon max values, and if your species is M is there and if your species N is there, and if your M has a corresponding lambda max at lambda 1 and N has a corresponding lambda max as lambda 2 only. Now, we should know the other absorbances also, which we can consider as the corresponding epsilon, not as maximum, but we can consider as epsilon mean or the epsilon in other wavelength. Okay. So, that is why we get this particular species for this epsilon of M and epsilon of N, which we are talking about the corresponding epsilon values at the max, but we know where we are writing is at the max, but we are taking this as the max, but when it is there, so it is at lambda 1. So, we will have another one also which will be at lambda 2, will be epsilon M2. Similarly, this one will be lambda 1 and this will be epsilon N at lambda 2. So, we will be handling or we will be using not only one epsilon max values, but for two components we will be handling 4 epsilon values. So, these are the 4 epsilon values, we should know the precise magnitude of these things. So, if we know separately, because one such example we can use or we can handle like this, that analysis of mixtures of two metal ions, analysis of mixtures of two metal ions, such that these are quite very normal, not very normal metal ions. One is palladium 2, another is gold 3. So, we have to choose some reagent for that. So, the name of this organic molecule is methiopmepragine. So, when methiopmepragine binds separately to this palladium 2 and gold 3, they can have their individual lambda max and epsilon max values. So, for these two, that means for the palladium 2 and the gold 3, so they have two maxima values like that of the indicators what we have seen just now in that particular way, that you have this one will be at 480 nanometer and other will be at 635 nanometer. So, this palladium 2 complex which has a corresponding epsilon max value at the lambda max at 480 nanometer, where epsilon value is 3550. Similarly, this gold 3 complex will have a corresponding lambda max value at 635 nanometer, having an epsilon value of 14,500. So, these are your epsilon values. So, this is also epsilon. So, this is one epsilon, this is another epsilon. So, we should know two other also, that means the corresponding absorbance of the palladium complex at the wavelength of absorption of gold 3, as well as the corresponding absorbance of gold 3 at the lambda max value of the corresponding palladium complexes, but these are very small values. So, it is 564 nanometer and this is 2960, sorry, epsilon values, mole inverse, centimeter inverse. Okay. So, these 4 quantities are very much essential. Then we can have the mixture of these two, and these two mixtures are basically reacting with this reagent, giving rise to the complexes of PdL2 and your gold L2, say. It can be PdL or gold L also if it is tetradentate one. So, it can be PdL or gold L also. So, you have the corresponding mixture and this mixture is taken and we can have this corresponding one, that means the total absorbances what we see over here, we will be able to measure these two absorbances A1 and A2. So, we can have the total absorbances. So, in a mixture of these two, what we do, we take give a 25 milliliter solution of this reagent. So, 25 milliliter of this reagent when it is added, that means this 25 milliliter of this reagent is an excess quantity. It is not that we are following a ratio of 1:2 for this type of complexation or 1:1 for this type of complexation, but we are putting this particular reagent is in excess. So, excess of this L we are adding, L is your this L, the ligand. So, L is in excess. So, that means the magnitude of this, that means whatever maximum amount of this ligand attaching to the metal ion center is formed and some free ligand will be there, but the free ligand is not giving us any trouble because your color absorbing species is the corresponding metal ion complexes. So, next we get this one and we dilute it to say 50 milliliter for our convenience. So, to a final 50 milliliter volume, and we can have this corresponding one and we measure this absorbances, that means A1 we measure and A2 we measure. So, A1 and A2 we have to measure. So, where it is A1? A1 is at 480 nanometer. So, this is the wavelength. So, this is at 480 nanometer, and where we will measure A2, A2 will be at 635 nanometer. So, we will be at 635 nanometer. So, these will be definitely nanometer and this will be definitely nanometer. So, the total absorbances we have to measure and the reading of these will be say in one case 0.533, in another case it is 0.590. So, what we see now that the absorbance values A1 and A2, if we can measure out of these. So, these two things, that means these two are in our data in our hand, and along with these things, by applying the equation for our these mixtures, we should be able to, that means we can have two equations out of that. forming these two, what we have seen just now, that A1 and A2, A1 and A2 is known, we can put these, and also we just know these values, that means cell and value B is known. Only thing, we can have two unknown concentration. One is the CPD 2 plus, that means is a small case c, concentration of palladium 2 plus, and another is CAU, small case, definitely concentration is always small case, AU 3 plus. So, these are the two unknown quantities what we can have, that one can be Cm, another can be Cn. Okay. So, this we have seen in these two these consecutive equations. What we see over here is that for your corresponding one, that means your this C, that means you see that Cm is here, Cm is also here, Cn and Cn. So, you have two unknown quantities. So, these are your two unknown quantities. We can solve these two equations to get your corresponding concentrations of this unknown palladium and unknown platinum. So, this is a typical methodology what we can follow for all these things, for your identification, and what we can do for now a continuous process, because these are the two individual things what we have monitored. That means, individually your palladium 2 plus and gold 3 plus you can measure, but if we can go like this, a titrimetric method, like your simple acid base titration, but we will take the spectrophotometer itself for that titration. That means, the cuvette of the spectrophotometer or the cuvette of the photometer is utilized for your reagent, that means your conical flux, reagent flux or the conical flux, where we can go for the typical titrations by simple burette or a micro burette also. So, what we do there, that one or more of the reactants or products, if they absorb nicely, what we have seen just now, it is the corresponding product which is absorbing the corresponding radiation. So, if the reactant or the product absorbs radiation, so far whatever we are discussing here is the products. The metal ion is reacting with your ligand, and that metal ion complex is your product, and product is responsible for your color. It can be your nickel DMG complex, it can be your corresponding lead carbazone complex, thiocarbazone, diphenyl thiocarbazone complex, all will be the corresponding product. Similarly, whatever example we have seen just now for your palladium and gold case, that means one reagent can give you two products, and those two products can absorb radiation. And that in other case also, the reactant can be colored. So, three things can be there in your hand. That means, either your reactant can be colored, that means your azo dye or your metal ion indicator, or your product can be colored. In that case, your chromophoric reagent is not colored, your product is colored. That means, the chromophoric product is your chromophore, and sometimes it is then absorbing indicator be added to the analyte solution, or we can add some analyte indicator such that there will be a change in the color for that particular reaction. So, that we can have the typical applications of these photometric titrations. Okay, so what we can apply? We can apply this particular one for the different photometric titrations. So, these are very much useful for your photometric detection. So, what we do these titrations, because we can go for the photometric detections of unknown analytes. Okay. So, these unknown. So, why these are very convenient, very useful, these things are, therefore, that we can have several measurements, not that only one measurement, because we can have 2, 3 measurements or 2, 3, 4 titrations, and we can take out the average of these. So, several measurements can be used. So, we can take the data from several measurements. So, those are very much useful because we can have the data and we can have 3 or 4 data in our hand. We can take the average of that such that we can get a more reliable data for this particular measurement, such that we can go for any unknown concentration of say palladium 2 plus, because this is our ultimate goal. How do we can get more precisely the unknown concentration of your palladium. So, the change of absorbance is being measured. So, because what we can measure, we are just monitoring the corresponding change in absorbances. So, change in absorbance we measured, and that is why we are going for this with the wavelength scan, that absorbances we are getting. So, for this particular reaction of this M plus L giving rise to corresponding ml, definitely some K is involved, the formation constant is involved for metal and complex formation. So, in this particular case, because most other cases for the precipitation reaction or the gravimetric estimation, we require a very large value of this Kf or the K formation. But in this particular case, the equilibrium constant for the reaction, that means the K need not be very large. It can be 10 to the power 5, 10 to the power 3 even to determine any unknown quantity of this palladium by some analyte giving a colored reaction. So, what we can find that if this is not there, that means if the K value is not required to be much also, and since the detection is not by manual, that means not by visual, not by our eyes. So, our eyes are not utilized to detect the color change or the intensity of the color. It is the detector of the spectrophotometer, detector of the which is being utilized. So, detector, the eyes are replaced by detector. So, we can use more dilute solution. That means, we can go down to a low concentration of say 10 to the power minus 3 molar, which we cannot do for usual manual titrimetric methods. Because in titrimetric method, most of the time we know from our school days that we are making some solution which can be n by 10, which can be n by 20, or sometime it can be up to m by 50. So, these are the most conventional and most useful concentration range what we do by simple titrimetric methods. But in this particular case, if your Kf is not required to be very large also. So, this particular one with the reaction with this reagent, and depending upon these absorbance values which are several thousands. So, we can go down to not even 10 to the power minus 3 molar, but we can go down to 10 to the power minus 4 molar or even 10 to the power minus 5 molar, which is the most conventional working range of concentration for fluorometric methods of analysis. That means, by using molecular fluorescence, we can go down to 10 to the power minus 5, 10 to the power minus 6 or 10 to the power minus 7 concentration. That we will see when we will talk about the molecular absorbances. So, these photometric titrations are very much useful in that way if we one of these species can be colored. So, like our conductometric titrations, what we see again from your the Skoog's book, that we can have all these different plots. So, nicely you see that all these plots, and whatever we are talking about here is some epsilon values only. And always we think we do something where that you have the corresponding analyte and all this. So, we can consider the corresponding epsilon values only for your corresponding species, that means the molar absorptivity of the substance titrated, that means your analyte, then the corresponding product or the titrant. Okay. So, the substance being titrated, the titrant and the product, if these are the corresponding epsilon values. So, any of them can give rise to your color. What we see that just if you have the metal ion Mn plus, which is reacting with the reagent, giving rise to the corresponding concentration of Ml. So, we can talk about in terms of the E epsilon of these, epsilon of these and epsilon of these. So, this is the very simple strategy for that, that you have the corresponding one, that means the absorbances, that means the corresponding absorbance, what absorbance we can talk about this particular species, and the corresponding thing that you can have the corresponding one, that means you can have the different absorbances for epsilon, for the metal ion, for the ligand and for the. So, any one can be very high. So, any one can be very high means that we can monitor these as the product, that means the product epsilon will be useful. But in some case your this reagent, the chromophoric reagent or the ligand can be useful, that means this value is high, or sometimes this can be very high, such that it can give rise to the decrease in the corresponding absorbance values. So, when the corresponding titrant, that means the titrant is only that epsilon value for the titrant is only greater than 0, and two other cases it is equal to 0, what we get that after the end point your absorbance will increase. And in this case also, if your the product is only increasing greater than 0, but if your other two are 0, so at the after the end point you have. So, what we basically get, like your conductometric titrations, we basically get, we should be able to detect this particular crossover. So, these crossover, this crossover, this crossover, this crossover and the other crossover. So, these are the most reasonable possibilities for all these titrations, what we can see for these things. So, any one of these, that means any one can be useful for your color absorption. So, we get this as your endpoint. So, when you go for this typical titration, this is your endpoint, this can be your endpoint, this can be your endpoint, this can be your endpoint. So, like your conductometric titrations, when you see the corresponding ionic conductance in the solution, the electrical conductance of the ionic solutions are changing, and there is a sharp change, what we call all these cases, that these are very sharp changes. So, sudden change, so this part is horizontal, then sudden increase is there. So, this is monotonically increasing, but after some time it is keeping horizontal, this is decreasing, then it is keeping horizontal, it is decreasing, then after the end point it is also increasing again. Then this particular thing, that means both the two parts, that means these two things are positive magnitude of your molar absorptivity is the increasing trend, but the magnitudes are different, because these two magnitudes are definitely different. They are greater than 0, but one will be very high. So, that means the positive slope in one case is less, in other case the slope is completely different. So, all these things will be very much useful for detecting that particular components. So, in this way also the photometric or spectrophotometric titrations, in our next class we will see that how we can handle this for a mixture of the metal ions. Just now we have taken one example of this palladium 2 plus and gold case for reacting with some reagent, but we should know or solving this particular simultaneous equations of that Lambert-Beer's law. But in our next class what we will see that a metal ion indicators, that means that EDTA titration we can do for a mixture of metal ions and how the corresponding photometric plots will look like. Okay. Thank you very much.